Welcome to class, students. In this class we discuss a generate statement used as a conditional, generate conditional statement. A generate conditional is like an if generate construct that permits the following Verilog constructs to be conditionally instantiated into another module based on an expression that is deterministic at the time of the design is elaborated. Okay. We'll understand what is elaboration. Elaboration means when your text code is executed, at that time the text code should be linked with the library files required and the operators that are defined. So entire thing, linking of all library files along with your text code, we call it as elaboration step. Modules, user defined primitives, gate primitives, continuous assignments, initial and always blocks. We'll see an example that shows an implementation of parameterized multiplier. In the example, if either there are two parameters a0 and a1, a0 width and a1 width parameters are less than 8 bits, a carry look ahead multiplier is instantiated. Now based on parameter width, see input width of a0 and a1, if it is less than 8 bits, carry look ahead adder should be used. If a0 and a1 width are greater than or equal to 8 bits, then a tree multiplier should be used. This is a given condition. Now it depends on the input parameter size whether to use carry look ahead multiplier or tree multiplier. We will not discuss much about the implementation of carry look ahead or tree multiplier design. We see only concentrate on how generate statement can be used as conditional statement here. If you see an example, okay, module name we are given as multiplier, product a0, a1 are the parameters, input a0 and a1 are inputs. We are defining parameters here, a0 width equal to 8, a1 width equal to 8. Local parameters, product width, if a0 is 8 bit, a1 is 8 bit, when you multiply 8 cross 8 data, so the maximum width of the product is sum of a0 and a1 widths, that is 8 plus 8 is 16. Product width will be 16 bit. This is a local parameter that we are defining. So within this module we can use this product width. And apart from that we have defined two parameters like constants. a0 width is 8, a1 width is 8. a0 and a1 are inputs whose size is 8 bit, means a0 width is 8, 8 minus 1, 8 minus 1 means 7 colon 0, 7 colon 0 means a0 size is 8 bit width. Here also a1 is also 8 bit in this example, so it is 7 colon 0. If you modify here less than 8, say 7, 6, accordingly the size will be adjusted. Only thing is we are changing value here, a0 width and a1 width. So if it is say 7, here 7 minus 1, 6 down to 0 it will be. a0 and a1 size will be 6 down to 0, which is nothing but 7 bits in size. Generate statement we are using as if else here. Generate if a0 width is less than 8 or a1 width is less than 8, in that case use a carry look ahead multiplier. You are sending parameters a0 width and a1 width, including this hash. m0 is m0 is instance name. Product is an output whose width depends on a0 and a1 width. a0 and a1 are actual parameters. So multiply values of a0 and a1, store in product. So this gate level instantiation is used within a generate statement. If a0 width and a1 width are equal to 8 or greater than that, in that case use tree multiplier. Here also you are performing a0 and a1 multiplication, you are storing in product. So end generate. What we have observed here is this particular code is executed and selection of carry look ahead multiplier or tree multiplier depends on the size of a0 and a1. The width of a0 and a1 will decide whether to use carry look ahead multiplier or tree multiplier. Implementation part of this multiplier we are not discussing. Here we have to concentrate on how we can use a generate statement as if else. So that we have seen. Generate start of the block. So since we are using only one statement, that is if else, no need to write begin and end here. End generate will indicate end of the generate block. At the time of this code execution, based on the a0 and a1 width, a particular multiplier block is selected for execution. So we have seen generate conditional using if else block. Now we'll see one more conditional statement using say case syntax. Case generate, within generate statement, a case statement how we can use. A generate case permits the following Verilog constructs to be conditionally instantiated into another module based on a select one of many case construct that is deterministic at the time the design is elaborated. Modules, user defined primitives, gate primitives, continuous assignments, initial and always blocks can be part of a generate case statement. We'll see example. Here module, module name is adder, sum and carry you need to generate, carry out sum, a0, a1 and carry n are the inputs. So those declaration part we have done here. Parameter n equal to 4 we are defining. So why we use parameter n equal to 4 in our coding is, if I change n value to 8, it will act as say 8-bit adder. If I change n to 2, it will act as 2-bit adder. So only thing is when we define parameters and use as part of coding, no need to change other portions of the coding. So when n becomes 8 here, automatically output size of sum will become 8-bit, a0 and a1 size will be defined as 8-bit, carry in and carry out size will be 1-bit. When n is 4, it will act as 4-bit adder, like that. 4 minus 1 down to 0, 4 minus 1 down to 0, a0, a1. Input Ci and C0 sizes, it remains 1-bit only. So to make it a general code, so we are defining parameter n equal to 4, parameter n we are defining, and within the code n is used instead of directly writing 3 down to 0. One more observation here. If suppose here I don't want to use parameter n equal to 4, that is also allowed. So instead, when you want to implement 4-bit adder, everywhere wherever n is used, n minus 1, that is Now here you can observe generate case statement syntax. Case n. N. Now this value of n will correspond. A default adder is carry locale adder. If n value is 1 bit, suppose, if n is 1 bit, then use the logic that we have defined for adder 1 bit. Adder 1 bit, instance name is adder 1. The logic written or module written for 1 bit adder should be used. When n is 2, a 2 bit adder implementation, this block need to be used. When n is more than 2, okay, in that case default carry locale adder should need to be used. This particular gate level instantiations, it depends entirely on the size of n. 1, 2, more than 2, default any value, use carry locale adder in this case. So a case statement is used as a part of a generate at the time of code execution based on the size of the A0 and A1 that we define here, that appropriately the module or the block is selected. So in this case it is n is 4, means it goes to default, it will select adder CLA. End case to indicate end of case statement. End generate, so only one statement is used, no need to write begin and end here. So here we are writing end generate to indicate end of the block. The block that is selected and implemented, it depends entirely on the time of execution based on the size of the inputs that we decide. If it is 1 bit, adder 1 bit module is selected. If it is 2 bit, adder 2 bit module is selected. If it is more than 2, in that case adder CLA is selected. This is how we need to use a generate case statement, and the appropriate module selection and implementation depends at the time of execution, that is simulation or synthesis. We will see one more example today's class, a 4-bit binary counter implementation. As name suggests, 4-bit binary counter, the output counter size is 4 bit. That means Q, which is our output, the size should be 4 bit, 3 down to 0. Clock and reset or clear signal size is 1 bit, those are defined as input. Output is redefined here. When we use always statement and you want to assign value to Q, in that case already we have seen output need to be redefined as a register. Output 3:0 is redefined as register 3:0 Q. Always add pause edge clear or negative edge of the clock. Pause edge of clear, when clear becomes 1, in that case Q should be 0, and whenever negative edge of the clock occurs, Q should be incremented by 1. Q assigned with Q plus 1. So here Q is defined as binary, 1 is integer. Q plus 1, binary plus integer, this is taken care. So initial value Q, say suppose when initial we clear it, Q will become 0, and then we make clear 0 for normal operation. In that case Q plus 1, on every negative edge of the clock or falling edge of the clock, Q is incremented by 1. So from 0 it will become 1 binary, then 2, 3, like that it goes on counting. Again when clear becomes 1, Q is assigned with value 0. Thank you students, we will continue in next class.